Inside the heart of a dying star, there is a kind of silence that no human ear could ever hear. A silence made of pressure, of collapsing heat, of the last moments of a titanic life that has burned for millions of years. Imagine descending into that fading star now, not drifting, but being drawn inward as the layers peel away. The outer envelopes, once bright, once swollen with fusion, are falling inwards like the pages of a book folding shut. As you move deeper, the familiar world disappears. At first, matter is still matter as we know it, atoms, ions, the ingredients of everything we touch. But gravity is tightening its grip. The star has exhausted its fuel, and without fusion to hold the collapse at bay, the core begins to compress with unstoppable force. Temperatures spike to billions of degrees. Atomic nuclei begin slamming together with energies that exceed anything our particle accelerators could dream of. And then, suddenly, the collapse tears reality into a new form. The first thing to break is the structure of the atom. Electrons are crushed into protons, forming neutrons and releasing a flood of neutrinos that escape outward in ghost-like torrents. The boundaries between particles begin to blur. Matter's delicate scaffolding shatters under pressure so intense that a teaspoon of it would outweigh mountains. If you could hold such a teaspoon, if your hand somehow survived the act, it would contain more mass than all the skyscrapers of New York City combined. We're now inside what used to be the star's core, but it no longer looks or behaves like anything familiar. This is neutron matter, a sea of neutrons packed together so violently that the idea of empty space disappears. To us, it seems like the end of structure, the end of form, the place where atoms give up. And yet, it might not be the end. If the star is just a little heavier, just a little more massive, then even the neutrons, those dense neutral particles, start to buckle. They too may break. The pressure climbs beyond comprehension, and quarks, the smaller particles inside neutrons, may be liberated, unbound, set loose in a kind of cosmic soup. This is the threshold where a quark star could be born. It's a place between two extremes, the neutron star, fiercely stable yet fragile in its own way, and the black hole, where even light can no longer escape. Between those two lies a razor-thin domain where matter might exist in a form so exotic that the universe rarely manages to create it, a realm where quarks are no longer confined in triplets, where matter is stripped past its limits, where physics reaches into the deep rules that govern the first microseconds of the Big Bang. A quark star, if it truly exists, would shine not with heat alone, but with a kind of defiance, a statement about the smallest building blocks of reality, a reminder that even in collapse there are stages of becoming that we're only beginning to imagine. What makes this threshold remarkable is not just the physics, but the emotion of it, the philosophical weight. It invites a question that feels ancient and strangely human. How far can matter be stripped before it stops being matter? Where is the boundary between structure and chaos? Between the tangible world we live in and the raw ingredients of existence? You can almost picture that boundary as a dim horizon, a transition zone inside the star where neutrons begin to melt under pressure so fierce it bends space-time itself. A place where the distinction between particle and fluid becomes blurred. Imagine the surface of such a star. No crust like a planet, no atmosphere like a sun, but an exposed ocean of quark matter, smooth, dense, and nothing like anything found on Earth. It might be only 12 kilometers across, smaller than many cities, yet it would contain more mass than our entire sun. Its gravity so intense that it would warp light around it in surreal, shimmering halos. And this leads us into the scientific mystery that makes quark stars so compelling. We don't yet know if they truly exist. They occupy a theoretical possibility, a narrow window in physics where the equations allow them to form, a window between too soft to remain neutrons and too hard to avoid becoming a black hole. The universe rarely balances on such fine edges, but sometimes it does, and when it does, it leaves clues, puzzling X-ray spectra, unexpected cooling curves, stars that rotate faster than our current models can easily explain. Before we move deeper into the science, into the equations, the observations, the theories stretching back to the 1970s, take a moment to ground yourself. We started inside a dying star, watching matter break apart layer by layer. We traced the collapse from atoms to neutrons and stepped into the possibility that even neutrons may not be the end. We followed the path of a star on the brink of becoming something stranger than physics once dared to consider. And as we explore this strange frontier together, this place where the universe rewrites the rules, if you enjoy drifting through cosmic mysteries like this, consider subscribing to the channel. Leave a comment letting me know where you're listening from and what time it is there right now. It helps this channel grow, and it keeps these quiet journeys alive. Now, as the collapse continues and the star approaches its final identity, we can widen the lens, move beyond the cinematic moment, and start asking what quark matter actually is, why it forms, and how we might detect a star made not of atoms or neutrons, but of liberated quarks. Everything we've known so far, the physics of matter, the structure of particles, the behavior of extreme forces, has brought us to this threshold. Now we can step over it and explore the world inside a quark star. When you shrink matter down far enough, when you peel back the layers of structure the universe has built into everything, from the air in your lungs to the mountains on Earth, you eventually reach the scale where atoms lose their meaning, not because they stop existing, but because they stop being the dominant language. Beyond atoms is a deeper architecture, one woven not of elements, but of the tiny vibrating punctuation marks of reality, quarks. A quark is not like anything in our everyday world. It isn't a miniature version of a particle you can picture. It doesn't orbit anything. It doesn't sit still. It doesn't resemble a sphere, a grain, a speck. It's a fundamental particle, one of the smallest units that physics recognizes as having internal identity. As far as our current understanding goes, quarks cannot be broken down into anything smaller. They are the end of the line for structure. There are 6 known types of quarks: up, down, charm, strange, top, and bottom. But in the dense, collapsed matter of the cosmos, only 3 concern us: up, down, and strange. These 3 flavors are the ones the universe leans on when it squeezes matter to its limits. The up and down quarks are the ordinary citizens of matter. Every proton and neutron you've ever encountered is made from combinations of these 2. A proton is 2 up quarks and a down quark. A neutron is 2 down quarks and an up. These triplets bind together so tightly that quarks are never found on their own in nature. They cannot wander freely. Instead, they are always imprisoned inside larger particles, what physicists call hadrons. If you ever wondered why you've never held a quark in your hand, or why scientists have never managed to isolate a quark in a lab despite decades of particle accelerator work, the answer lies in a phenomenon that sounds poetic but is deeply, technically unforgiving: color confinement. The term color in physics doesn't refer to color as humans see it. It's a mathematical property, a kind of quantum identity assigned to quarks. Each quark carries one of 3 color charges: red, green, or blue, chosen simply because the analogy to visible color mixing helps conceptualize how quarks combine. When quarks form a stable particle like a proton, their colors must combine to what physicists call white, meaning a balanced, neutral state, just as combining red, green, and blue in the right proportions on a digital screen produces white light. The strange part is not the color system, it's the confinement. If you try to pull 2 quarks apart, the force between them grows instead of weakens. It's like stretching a rubber band that becomes stronger the farther you pull. The more you try to tear a quark away from its partners, the more resistance the universe applies. Eventually, the energy you're putting in becomes so great that instead of separating the quarks, the energy converts into new quark-antiquark pairs. The original quarks remain confined. The system prefers to create new matter rather than let a quark escape. This is why, in all of human history, we have never seen a free quark. As far as we know, they can't exist alone under ordinary conditions. They exist only inside the particles they create by sticking to one another. But the universe has a habit of placing ordinary conditions in quotation marks. Inside a neutron star, or deeper still, in the collapse that might create a quark star, the pressure does something extraordinary. It doesn't pull quarks apart. It crushes them together so violently that the boundaries between their host particles begin to dissolve. Neutrons squeeze so tightly that their internal quarks feel the presence of quarks in neighboring neutrons. Eventually, the distinction between this neutron and that neutron stops being meaningful. This is what physicists call deconfinement. It's the moment when quarks stop belonging to individual particles and begin to flow collectively, like liquid droplets merging into a single ocean. They're no longer stuck in trios. They are free, not because they escaped, but because the prison dissolved around them. Deconfinement is not gentle. It requires pressures and densities so extreme that they only occur in the universe's most violent environments. The instant just after the Big Bang, in the collisions of heavy ions inside particle accelerators, and possibly in the cores of massive neutron stars before collapse. To reach this state in a laboratory, scientists slam gold or lead nuclei together at nearly the speed of light inside machines like the Large Hadron Collider and the relativistic Heavy Ion Collider for an unimaginably short instant. Less than a trillionth of a second, the energy density becomes high enough to melt protons and neutrons into pure quark matter. This fleeting essence is called quark-gluon plasma, the hottest and densest form of matter humans have ever created. It is not merely warm. It reaches temperatures of around 4 trillion degrees Celsius, hundreds of thousands of times hotter than the core of the sun. It behaves like a nearly perfect fluid. It flows with almost no resistance, slipping across itself in ways that defy conventional intuition. This plasma is a glimpse of what the universe looked like just after its birth, when it was so hot that particles couldn't form stable structures. Comparing this laboratory plasma to the interior of a collapsed star feels both intuitive and deceptive. In accelerators, the quark-gluon plasma is extremely hot, but not particularly dense. In neutron star interiors, the quark matter, if it forms at all, is extremely dense, but relatively cool by cosmic standards. The universe, in its endless creativity, has two different roads to deconfinement. Blast particles apart with heat, or crush them together with pressure. One way tears matter open, the other squeezes it into unity. If quark matter exists inside a neutron star or forms an entire quark star, it would be cold compared to collider plasma, just millions of degrees, not trillions. Yet its density would be extraordinary. Imagine all the atoms in Mount Everest crushed into a sphere the size of a marble. Then imagine that marble being one grain in a sea of such marbles, each one a cluster of quarks now liberated from their triads. That's still an understatement. What's remarkable is how quark matter behaves in this compressed astrophysical form. Theoretical calculations suggest that quarks, once freed, may arrange themselves into an exotic, nearly frictionless liquid. There may be no structural crust in the normal sense, no lattice of nuclei, no layers of electrons or ions. Instead, just a deep, self-bound sea of quarks, up, down, and perhaps strange, moving collectively. The strange quark deserves a moment of attention. It is heavier than up and down quarks, but still light enough to appear naturally in extreme environments. Under the crushing pressure inside a neutron star core, down quarks may transform into strange quarks, producing what physicists call strange quark matter. The term strange was chosen long before anyone knew it might literally describe something from the heart of a collapsed star. The universe has a talent for naming things with accidental poetry. The idea that strange quark matter could form is tied to a bold proposal called the Bodmer-Witten hypothesis. It suggests that strange matter might actually be more stable than ordinary nuclear matter. If true, this would mean that quark matter, specifically strange quark matter, is not just an exotic byproduct of collapse. It could be the true ground state of matter, the most energetically favourable form the universe can arrange itself into. If that sounds unsettling, don't worry. Even if strange quark matter is stable, it still requires immense pressure to form. The universe prevents it from spontaneously appearing on your kitchen table. The physics behind these ideas has roots in work from the 1970s and 1980s, when physicists first tried to understand how quantum chromodynamics, the theory describing quarks and the force that binds them, behaves under conditions far beyond what experiments could test. Over time, computational breakthroughs and astrophysical observations began to converge, hinting that compact stars might hold the answers. Quark matter doesn't exist in our world, not in the air, not in metals or living tissue. It belongs to the inner realms of collapsed stars, or the first milliseconds after the Big Bang. It is the matter of extremes, of boundaries, of transitions. And yet, for something so remote from ordinary experience, it has an oddly simple essence. Quarks, freed from confinement, sharing a single collective home. When matter enters this state, it sheds the familiar architecture that defines the universe as we know it. Bonds dissolve, identities shift, and the most fundamental ingredients arrange themselves into an entirely new order. It is a reminder that the cosmos keeps secrets in places where pressure and density rewrite the rules, where the smallest building blocks reveal forms of existence that defy what we consider ordinary. Massive stars live with a kind of arrogance. They burn brighter, fuse heavier elements, and die more violently than smaller stars ever could. Their lifetimes are short by cosmic standards, just a few million years, but during that time they behave like colossal engines, crushing hydrogen into helium, helium into carbon, carbon into oxygen, and onward through the periodic table. Each fusion stage supplies outward pressure against gravity, balancing the star like a perfectly poised dance between explosion and collapse. Yet even the heaviest fusion reactions have a limit. Past iron, fusion no longer yields energy, it consumes it. When a massive star finally builds an iron core, the balance falters. Gravity begins to win. The core contracts, temperatures rise to tens of billions of degrees, and the final moments of the star's life arrive with breathtaking speed. Inside the collapsing core, electrons are forced into protons, creating neutrons and releasing an enormous burst of neutrinos, those ghost-like particles that slip through matter as though it barely exists. In less than a second, the core compresses into something unimaginably dense. Once the neutrons can pack no closer, their quantum degeneracy halts the collapse, and the outer layers rebound off this suddenly rigid core. The result is a supernova explosion that can outshine an entire galaxy. The explosion ejects the star's outer layers into space, creating shockwaves that sculpt nebulae and seed future star systems with heavy elements. What remains behind is a compact object, its nature determined by the mass of the collapsed core. If the core is below a certain threshold, it becomes a neutron star. If it is above another threshold, it collapses directly into a black hole, vanishing from the observable universe behind an event horizon. Between these outcomes lies a narrow and fascinating possibility. A star core slightly too heavy for a stable neutron star might compress past the point where neutrons remain intact. The neutrons begin to melt, not from heat alone, but from overwhelming pressure. The density surpasses that of any atomic nucleus, and quarks, normally confined inside neutrons, spill into a shared, deconfined sea. The birth of quark matter is not gentle. It begins as a small, dense kernel at the centre of the neutron star, where pressures are highest. This kernel grows outward as more neutrons collapse into their constituent quarks. If conditions are right, the strange quark may appear, transforming the quark matter into a more stable blend of up, down, and strange quarks. In this scenario, the conversion front spreads through the star like a slow inward flame, not of fire, but of phase transition. Theoretical calculations suggest this transformation is explosive at a microscopic scale. Each cluster of neutrons that converts releases a flood of neutrinos and heat, raising local temperatures to tens of trillions of Kelvin. This is far hotter than any natural environment in today's universe, rivaling temperatures from the first microseconds after the Big Bang. The newly created quark matter behaves like a fluid so dense that even atoms lose identity, a collective ocean of fundamental particles. One of the remarkable nuances of this process is the role of neutrinos. During the initial core collapse of the supernova, neutrinos carry away an enormous amount of energy, roughly 99% of the gravitational potential released. In the hypothetical quark star birth, neutrinos again become the silent messengers of transformation. As the neutron matter converts into quark matter, neutrino bursts surge outward from the conversion front. These bursts could, in principle, be observable if the event were close enough to Earth. They would arrive before any electromagnetic signal announcing the transformation with a whisper that only neutrino detectors could hear. In the models that predict this transformation, the quark core grows until it engulfs the entire object. The star becomes what physicists call a strange star, composed entirely of strange quark matter. This is not strange in the sense of odd, though it certainly is. It's strange in the sense that strange quarks are part of its composition. If the Bodmer-Witten hypothesis is correct, that strange quark matter may be more stable than nuclear matter. Then once the transformation begins, it becomes energetically favourable for the whole star to convert. The transformation has consequences for the star's size, magnetic field, and cooling behaviour. In theory, a strange star would be slightly smaller than a neutron star of the same mass due to quark matter's ability to compress more tightly. Its surface might lack the familiar crust of nuclei found on neutron stars, leaving an exposed sea of quark matter with unusual electric fields at the boundary. The star's cooling rate would differ as well. Quark matter radiates energy in unique ways, with neutrinos carrying away heat far more efficiently. Whether this transformation is gradual or explosive remains a matter of debate. Some models propose a gentle, wave-like transition. Others suggest a quark nova, a second catastrophic explosion following the supernova. In the latter scenario, the conversion releases enough energy to eject the star's outer crust at high velocity. Such an event could produce a distinctive light curve, a bright, rapidly evolving burst unlike ordinary supernovae. Astronomers have looked for such signatures, and a handful of unusual transient events have been proposed as possible quark novae candidates, though none are confirmed. There is also the question of rotation. Many neutron stars spin rapidly, completing dozens or even hundreds of rotations per second. As the core contracts into quark matter, the star's moment of inertia changes. Like a figure skater pulling in their arms, the star could spin faster. Some researchers argue that sudden jumps in rotation, known as glitches, could hint at internal transitions related to quark matter. These ideas remain speculative but intriguing. The birth of a quark star is not a simple branching in stellar evolution. It is a rare path, requiring the star to land precisely between stability and collapse. Too little mass, and it remains a neutron star. Too much, and it falls into a black hole. The universe must operate within a finely balanced window, one where the collapse presses quarks into freedom, but does not push them beyond the point of no return. To imagine this balance, picture a star whose core density approaches 10 times that of nuclear matter. Inside, neutrons are pressed together so tightly that their internal quarks begin to overlap. The quantum pressure that once held the neutrons apart can no longer resist gravity. The neutrons blur into one another and the quark cores merge. At this stage, matter no longer behaves like a gas of neutrons. It becomes a fluid of quarks, each gliding through a collective medium with no distinct boundaries. The temperature spikes to truly astonishing levels, momentarily reaching tens of trillions of Kelvin. Under such conditions, the strong nuclear force acts differently, binding quarks into new combinations even as the original triplets dissolve. The gluons, the carriers of the strong force, play a central role here, stitching the quark matter together in a dynamic, constantly shifting network. This is the quark-gluon plasma of the early universe, born again in the heart of a dying star. But unlike the quark-gluon plasma created in particle accelerators, which lasts for mere fractions of a second, the quark matter inside the star can persist. Supported by pressure and gravity, the star becomes a stable configuration, a celestial object made of quark fluid, possibly superconducting and superfluid at the same time. There is a subtle beauty in this process. A star that once fused hydrogen in gentle cycles ends its life as a compact sphere of fundamental particles, an object that bridges the physics of the everyday universe and the physics of the universe's birth. It is the transformation of matter into its most elemental form, not by taking it apart, but by forcing it into unity. The formation of a quark star represents a moment when nature pushes against the boundaries of stability, exploring a state of matter that is normally hidden behind confinement. It shows that collapse is not always annihilation. Sometimes it is a route to a deeper order, a new identity born from pressure so extreme it reshapes the architecture of existence. And in that transformation from a burning sphere of fusion to a dense globe of quark matter, the universe demonstrates that endings are rarely simple. They can be violent, beautiful, and deeply revealing. A neutron star is already one of the most extreme objects known to physics, a place where matter is pressed to the edge of possibility. And yet, if quark stars exist, they represent a step even further, an escalation into a realm where structure dissolves and the universe reveals new forms of organization. To understand the difference between these two objects, it helps to picture them not as distant astrophysical curiosities, but as two stages in a progression. One built from the broken remains of atoms, the other from the broken remains of neutrons. A neutron star begins with neutron-degenerate matter. This substance is astonishing in its own right. Imagine packing more mass than the Sun into a sphere just 20 kilometers, about 12 miles, across. Gravity squeezes the star so fiercely that electrons are forced into protons, forming neutrons and releasing neutrinos that escape into space. What remains is matter dominated by tightly packed neutrons, each governed by the quantum mechanical rules that forbid identical particles from occupying the same state. This quantum degeneracy pressure is the only thing resisting further collapse. Inside the crust of a neutron star, there is still some structure. The outer layers consist of a dense lattice of nuclei, surrounded by a sea of electrons. Moving inward, the crust transitions into a region where neutrons begin to drip out of nuclei, forming a superfluid that threads through the crystalline structure. Deeper still, the nuclei break apart entirely, leaving a fluid of neutrons with a scattering of protons and electrons. The core is a place of strangeness, neutrons packed so densely that they behave less like individual particles and more like an overlapping soup. In this extreme environment, new forms of matter may appear. Hyperons, particles containing strange quarks, could emerge as the density increases. The creation of hyperons is energetically favourable once neutrons become so tightly squeezed that adding a strange quark lowers the overall energy of the system. This possibility has profound implications. Hyperons soften the equation of state, making the neutron star more compressible. If hyperons appear, they reduce the maximum mass the neutron star can support before collapsing into a black hole. Hyperons introduce attention in neutron star physics. Many observed neutron stars are heavier than two solar masses, yet hyperonic equations of state often struggle to support such masses. This hyperon puzzle is one of the reasons quark matter becomes an appealing solution. If the core transitions into deconfined quark matter before hyperons fully dominate, the star might regain stiffness, ironically becoming more resistant to collapse than a hyperon-rich neutron star. The idea of a quark matter core has gained traction over the past 2 decades. In this picture, neutron stars are not uniform. They have a layered structure, a nuclear matter outer region, and a core where quarks flow freely. The size of this core depends on the star's mass. Lower mass neutron stars may have no quark matter at all, while heavier ones might host a substantial core. As conditions grow more extreme, the balance can tip further. A star that collapses into quark matter at its center may eventually transition completely. Instead of a neutron star with a quark core, it becomes a quark star, a self-bound object composed entirely of quark matter. In such a star, neutrons no longer exist as particles. The building blocks are quarks themselves, arranged into an exotic fluid dominated by up, down, and strange quarks. This transition profoundly alters the internal structure. A neutron star depends on gravity squeezing the nuclear matter inward. A quark star depends on the pressure generated by the quark matter itself. In the latter case, the matter is so tightly bound that the star is self-supported even without gravity's inward force. This means quark stars could theoretically remain stable at much smaller sizes than neutron stars. The density inside these stars is almost incomprehensible. A typical neutron star has an average density of around 3 × 10 to the 17th kilograms per cubic meter, roughly the density of an atomic nucleus. A quark star is even denser. In some models, the density increases by another factor of 2 or 3. At the center, it may reach up to 1 × 10 to the 18th kilograms per cubic meter. Comparing these densities to any earthly substance is hopeless. The analogy that a teaspoon would weigh a mountain is not exaggeration, but understatement. These internal differences influence the star's external behaviors. Rotation, for instance, provides clues. Neutron stars can spin extremely quickly, particularly when they accrete material from a companion star. Some pulsars rotate more than 700 times per second. If quark stars exist, they could spin even faster. Because quark matter can be compressed into a smaller radius while maintaining mass, the star's moment of inertia changes. A smaller radius allows for more rapid rotation before the star reaches the breakup limit where centrifugal forces tear it apart. A related phenomenon involves glitches, sudden changes in rotation speed detected in pulsars. Neutron stars exhibit these glitches when their superfluid interiors transfer angular momentum to the crust. In a quark star, the behavior would differ. A quark star may lack the kind of solid crust needed to create the pinning and sudden release associated with glitches. If a quark star does have a crust, it would be extremely thin and likely composed of a strange arrangement of nuclei suspended above the quark matter surface by electric fields. Glitches in such an object would follow different patterns, potentially giving astronomers a way to distinguish between the two types of stars. Magnetic fields provide another lens into the differences. Neutron stars are born with magnetic fields that can be trillions of times stronger than Earth's. In magnetars, these fields reach values up to 10 to the 11th power teslas, strong enough to distort atomic orbitals and make empty space behave like a birefringent medium. If quark stars exist, their magnetic fields may be even more complex. Quark matter could enter a phase known as color-superconductivity, where quarks pair up in analogues of Cooper pairs from ordinary superconductors. These quark pairs behave collectively, and the resulting state can expel magnetic fields or trap them in quantized flux tubes depending on the specific phase. A color flavor locked CFL phase, for example, might force magnetic fields into discrete structures threading the star. These patterns would influence the star's emission, possibly producing detectable signatures in its X-ray or gamma-ray output. There is also a difference in how these stars cool. Neutron stars cool largely through neutrino emission in their early life, transitioning to photon cooling at later stages. Quark stars would cool more rapidly. Neutrino emission processes in quark matter are more efficient, allowing heat to escape faster. Some neutron stars observed to be cooling unusually quickly have been proposed as potential quark star candidates, though the data remains equivocal. Another distinction lies in their mass-radius relationships. Neutron stars follow a particular curve. As they gain mass, their radius shrinks, but only to a point. Beyond roughly 2 solar masses, most equations of state predict collapse into a black hole. Quark stars, being self-bound, follow a different trend. Their radii can be much smaller for the same mass. A neutron star of 2 solar masses might be 12 kilometers, about 7 miles, across. A quark star of the same mass could be 9 or 10 kilometers, about 5.5 to 6 miles. This difference, just a few kilometers, may be subtle, but for astronomers modelling pulse profiles, gravitational redshift and tidal deformability, it could be detectable. Tidal deformability, the ease with which a star's shape is distorted by a gravitational field, has become a crucial tool thanks to gravitational wave astronomy. When 2 neutron stars spiral together and merge, the way they stretch and squeeze one another leaves imprints on the gravitational wave signal. These imprints are sensitive to the star's internal structure. Quark matter cores or fully quark-dominated stars would respond differently to tidal forces than neutron stars made entirely of nuclear matter. In these collisions, a star with a quark core might show distinct signatures in the merger dynamics: faster collapse to a black hole, different oscillation frequencies, or altered ejector mass. These details remain difficult to measure with current detectors, but future observatories may provide the clarity needed. Comparing neutron stars to quark stars reveals a spectrum of possibilities rather than a simple binary. A star could be entirely composed of nuclear matter, contain a quark core, exist as a hybrid of multiple phases, or be fully dominated by quark matter from center to surface. The boundary between these states is not clean. It is a set of transitions dictated by density, temperature, pressure, and the fundamental physics of quarks. If quark stars exist, they extend the narrative of how matter behaves under extreme conditions. They show that even after atoms collapse into neutrons, the story isn't finished. The universe has deeper layers, hidden behind densities so extreme that the particles forming the structure of ordinary matter are not just rearranged, they are unbound, liberated into a new form of existence. Among the many exotic ideas in astrophysics, few have the unsettling elegance of strange quark matter. It sits at the crossroads of particle physics and stellar death, hinting at a possibility that sounds almost philosophical, that the matter we're made of, the neutrons and protons at the core of every atom, might not be the most stable form of matter the universe can create. Strange quark matter, often called SQM, is a theoretical mixture of up, down, and strange quarks blended into a single uniform fluid. It isn't built from individual particles the way ordinary matter is. Instead, it behaves like a continuous sea of quarks in which the usual boundaries between particles vanish. Under the tremendous pressures inside a collapsing star, up and down quarks may convert into strange quarks, creating a mixture that can potentially settle into a lower energy state. This idea gains its strongest form in what is known as the Bodmer-Witten hypothesis, proposed independently by physicist Arnold Bodmer in 1971 and later expanded by Edward Witten in the 1980s. The hypothesis makes a bold claim: Strange quark matter might be the true ground state of matter. In other words, the universe may preferentially want to arrange quarks in the form of this three-flavor mixture. If so, all ordinary matter, atoms, nuclei, even neutron stars, would be metastable. They would exist only because the pressures required to turn them into strange matter are rarely achieved naturally. The notion that the most stable form of matter could be something we almost never encounter is both thrilling and unnerving. It would mean that neutron stars, normally considered some of the universe's most stable objects, might themselves be only local minima in the vast landscape of possible states. Push them hard enough, compress them just a bit further, and they could collapse into something denser, more symmetrical, and more uniform. A strange star. The idea of stability is subtle here. Strange quark matter is predicted to be stable only at extremely high densities. On Earth, where matter is sparse by comparison, SQM would likely fall apart into ordinary nuclei. Only under pressures far exceeding nuclear density can quarks merge into the collective ocean that SQM requires. This is why the hypothesis doesn't imply that everyday matter is at risk, or that the atoms in your body are secretly longing to turn into quark soup. The transition requires conditions so extreme that only the hearts of dead stars can provide them. In the theoretical picture, strange matter forms when a neutron star's core becomes dense enough for down quarks to convert into strange quarks via the weak nuclear force. This conversion reduces the system's energy, making the resulting mixture more stable. Once a pocket of strange matter forms, something remarkable could happen. It may begin to grow. The conversion of neutrons to strange matter is energetically favourable, meaning the process could spread outward like a front, slowly transforming the star from the inside. The result would be a strange star, an entire celestial object made not of neutrons, but of a seamless expanse of quark matter. A strange star differs from a neutron star not only in composition but in structure. The matter inside is self-bound, held together by the strong force rather than gravity alone. This means strange stars can be smaller than neutron stars of equal mass. They may have sharp surfaces where quark matter abruptly ends, unlike neutron stars' layered, crusted structures. In some models, a strange star might have no crust at all, a bare surface of quark matter, with electric fields so intense they could strip electrons from atoms trying to land on it. This brings up one of the most incredible implications of the SQM hypothesis, the possibility of conversion. If a fragment of strange matter, a strangelet, were to touch ordinary nuclear matter under the right conditions, it could theoretically trigger a chain reaction, converting nearby nuclei into strange matter. This idea has fueled decades of speculation, from serious physics papers to far-fetched science fiction scenarios. Fortunately for human anxiety levels, the physics strongly suggests that this conversion cannot occur under normal circumstances. Strangelets, if they exist at all, would be stable only under extreme pressure. Released into normal density environments, they would decay rapidly. Experiments at particle accelerators, where strange quarks sometimes appear briefly in high-energy collisions, have never produced stable strangelets. And cosmic ray impacts on neutron stars, far more energetic than anything humans can create, have not triggered widespread conversions, a fact that strongly reassures physicists that large-scale conversion does not happen easily. Still, the idea retains its power because it touches on something deep, the possibility that the nature of matter is more flexible than our everyday world suggests. Strange quark matter is a reminder that stability is not an absolute concept. It depends on environment, density, and the symmetries of the fundamental forces. Matter that is perfectly stable on Earth might be temporary or fragile in the heart of a collapsed star. A strange star, if it exists, would behave differently from any neutron star. Its cooling curve would be distinct because quark matter emits neutrinos more efficiently. Its surface would interact with surrounding magnetic fields in unfamiliar ways. Its rotational properties might deviate from neutron star models, with faster spins possible due to smaller radii. Its seismic behavior, starquakes, oscillations, and internal vibrations, would follow entirely different rules, governed by the dynamics of quark matter rather than crusted nuclear layers. Even its light would carry clues. A bare, strange star might emit photons through a thin electron atmosphere, producing spectra unlike anything neutron stars typically generate. Some of the smooth, featureless X-ray spectra observed in a few compact stars have been tentatively proposed as hints of strange star candidates, though none are confirmed. Strange quark matter also has profound implications for cosmic evolution. If the early universe produced SQM during the quark-gluon plasma phase, small nuggets might have survived the cosmic expansion. These hypothetical relics, drifting silently through space, could be remnants from the first milliseconds after the Big Bang. They would be incredibly dense, incredibly stable, and incredibly rare, if they exist at all. The elegance of the Bodmer-Witten hypothesis lies in its simplicity. It does not require exotic new physics. It arises naturally from the behavior of quarks under the strong force. Yet its consequences stretch across scales, from subatomic particles to entire stars. It suggests a universe where matter, when pushed hard enough, settles into an unexpectedly symmetrical state, one where distinctions between particles dissolve and quarks share a common home. In a sense, strange quark matter is a story about unity. The boundaries between neutrons, protons, and quarks disappear. The star becomes a single, continuous entity, held together by the same force that binds the nuclei of atoms, but acting on a vastly grander scale. It is a vision of matter, stripped to its essence, not chaotic, but organized, not broken, but reformed into a deeper, more fundamental order. Whether strange stars truly exist or remain only a theoretical possibility, they challenge our understanding of what matter can become when the universe pushes it beyond the limits of structure. They remind us that even in collapse, there can be new forms of stability, states hidden behind pressures so extreme that only the most violent events in the cosmos can reveal them. The surface of a quark star is one of the strangest concepts in astrophysics. It defies intuition because it isn't a surface in the way planets have surfaces, or even in the way neutron stars have crusts. A quark star's outer boundary is the meeting point between the most extreme form of matter the universe can sustain and the vacuum of space. It is a frontier where the rules that govern atomic structure no longer apply, where quark matter presses directly against emptiness, and where the forces that define everyday physics are stretched to their limits. To imagine such a surface, start with what it is not. It is not made of atoms. It does not consist of iron nuclei packed into a crystalline structure like the crust of a neutron star. It is not coated in the familiar layers of electrons interacting with magnetic fields. Instead, at its most extreme, it might be bare, an exposed ocean of quarks, held together by the strong nuclear force itself. This is the bare quark star, the purest and most radical version of the concept. In a bare quark star, the quark matter reaches all the way to the boundary. There is no crust of normal nuclear material. Instead, a thin layer of electrons hovers above the quark surface, held in place not by gravity, but by electrostatic forces. The quark matter below is charged slightly positively, the electron layer slightly negatively, forming an enormous electric field, an electric barrier so strong it dwarfs any field producible by human technology. Some estimates place the field strength at over 10 to the 17th power volts per meter, a value so extreme that it challenges the very notion of what an electric field can be. This electric barrier prevents ordinary nuclei from touching the quark matter. If atomic nuclei were allowed to contact the surface directly, they might be converted into strange quark matter, releasing energy and potentially infecting nearby material. But the electric layer stops this from happening under normal conditions. It acts like a shield, a kind of force field generated naturally by the properties of quark matter itself. Just above the quark surface, electrons form what is essentially an atmosphere only a few hundred femtometers thick. That's on the scale of the size of a nucleus, a thickness so small that if the star were the size of Earth, this atmosphere would be thinner than a single molecule. Beneath it, the quark matter sits as a smooth, sharply defined surface. There is no rocky terrain, no mountains, no cracks. The idea of ground doesn't apply. This is a flawless, uniform plane of quark fluid, smooth in a way no ordinary material could ever be. But not all quark stars are necessarily bare. In some models, a thin crust of normal nuclear matter may form above the quark surface, suspended by the intense electric field between the quark matter and the electron layer. This crust might resemble the outer layers of a neutron star, with a lattice of nuclei embedded in a sea of electrons. But unlike a neutron star crust, it would be limited in thickness and mass. The electric repulsion prevents the crust from sinking into the quark matter below. It floats above the surface like a fragile shell, only a couple hundred meters thick, tiny compared to the star's radius. This crusted scenario changes the star's observable properties. A crusted quark star would show different cooling behavior, and the crust could store elastic energy, allowing for starquakes and rotational glitches, similar to those seen in neutron stars. A bare quark star, by contrast, would lack the kind of solid structure required for such events. Its surface dynamics would be dominated not by crustal fractures, but by phenomena occurring in the quark-electron interface and the intense electric field at the boundary. No matter whether the surface is bare or crusted, the early life of a quark star is extraordinarily hot. In the first fractions of a second after formation, the temperature can soar to tens of trillions of Kelvin, rivaling the conditions of the universe's first microseconds. This heat is a byproduct of the violent conversion of neutrons into quark matter, a process that releases vast energy, mostly in the form of neutrinos. As the star cools, the temperature drops rapidly. Within seconds, the outer layers may fall from trillions of Kelvin to billions, and over the next minutes to hours to millions. This rapid cooling is one of the signatures that astronomers search for. Quark matter emits neutrinos far more efficiently than nuclear matter. The star loses heat faster, and the surface temperature plummets at a rate that differs from standard neutron star cooling curves. Some compact stars that appear unexpectedly cool for their age have been considered potential quark stars for this reason, though the evidence remains inconclusive. Another dramatic phenomenon at the surface is the potential evaporation of strangelets, tiny droplets of strange quark matter. In the early moments after birth, the surface may be hot enough that small parcels of quark matter are shaken loose. These fragments, if they survive, could be ejected into space and drift as microscopic nuggets. Whether such strangelets could remain stable outside the star depends on their size and the density of their environment. Most would decay rapidly, but some theories allow for stable strangelets that might survive long enough to travel through the galaxy. This evaporation, if it occurs, would release distinctive radiation. The strangelets would carry away charge and energy, producing electromagnetic signatures that differ from any known particle process in neutron stars. Detecting such signals would be an extraordinary breakthrough, providing direct evidence of quark matter outside a stellar interior. The surface also interacts with magnetic fields in ways no ordinary star can. Neutron stars already have extraordinary magnetic fields, but quark matter, especially if it enters a color-superconducting phase, can modify these fields dramatically. Some phases allow magnetic fields to pass through in quantized tubes, others expel fields entirely, creating complex patterns that warp the star's emission. The boundary between quark matter and the electron layer can generate unusual plasma behavior, altering how charged particles accelerate in the star's magnetosphere. These interactions affect the star's spectrum. A bare quark star might emit a nearly featureless thermal spectrum, lacking the atomic absorption lines found in neutron stars with atmospheres. The surface is not composed of atoms, so there are no atomic transitions to imprint on the light. Instead, the radiation comes from the electron layer, which produces smoother, simpler spectra. Several compact stars observed with unusually featureless X-ray spectra have sparked discussions about whether they might be bare quark stars, though there are alternative explanations as well. Crusted quark stars, on the other hand, may show more complex spectra depending on the composition of the suspended crust. But even these spectra would differ subtly from those of neutron stars, shaped by the electric field, the thinness of the crust, and the altered thermal properties. The quark star surface also influences how the star interacts with incoming material. If gas from a companion star falls onto a bare quark star, it encounters the intense electric field at the boundary. Instead of piling up, the material may be repelled, accelerated, or vaporized. Accretion onto a quark star would produce different X-ray signatures and could potentially create bursts or flares that reveal the star's nature. One of the more intriguing possibilities is that a bare quark surface could exhibit sharp spectral edges, sudden cutoffs in emitted energy caused by the strong electric field's interaction with electrons. These edges would not resemble anything produced by nuclear matter. If observed, they would offer a clear signal that the star's surface is not composed of atoms or ions, but something more fundamental. Every aspect of a quark star's surface reflects a deeper truth. The boundary is not a place where matter transitions smoothly from one phase to another. It is a discontinuity, a sudden shift from a fluid of deconfined quarks to the vacuum of space. No other object in the universe is believed to have such a boundary. Even black holes, with their event horizons, have surfaces defined by space-time geometry rather than physical matter. A quark star's surface is an encounter between two extremes, the strongest force in nature acting inside and the emptiness of the cosmos outside. That boundary may hold the clues astronomers need to finally distinguish quark stars from neutron stars. Whether through cooling curves, spectral signatures, strangelet evaporation, or magnetic anomalies, the surface is where the star speaks to the universe. And if these signals are ever detected clearly, they will reveal not just a new kind of star, but a new state of matter, one that has existed since the beginning of time, hidden until the universe's most violent moments bring it briefly into view. Quark matter is already an extreme idea, but the universe rarely settles for extremes that are merely ordinary. When quarks are squeezed tightly enough, under pressures so immense that they move collectively rather than as distinct particles, they begin to behave in ways that defy familiar categories. One of the most remarkable possibilities is that quark matter may enter a superconducting state. Not a superconducting state of electrons, like the materials cooled in laboratory cryostats, but a superconducting state of color charge itself, governed by the strong nuclear force. This phenomenon is known as color-superconductivity, and it represents one of the most exotic phases of matter ever proposed. To understand how this works, it helps to consider why superconductivity occurs at all. In ordinary materials, electrons can pair up into what physicists call Cooper pairs. These pairs move through a crystal lattice without resistance, forming a supercurrent that persists indefinitely. The mechanism relies on attractive interactions at extremely low temperatures, fractions of a degree above absolute zero. In quark matter, something conceptually similar happens, but at densities and energies unimaginably greater. Quarks carry not only electric charge, but color charge, the quantum property that makes them interact via the strong force. Under extreme compression, quarks can form pairs just like electrons do, but these pairs involve color interactions rather than phonons in a crystal lattice. The result is a state where color charge flows effortlessly, forming a perfect color superconductor. The simplest of these quark-paired states is the 2sc phase, short for two-flavor superconducting. In this phase, up and down, quarks pair up in certain color combinations, while strange quarks remain unpaired, either because they are too heavy or because the density isn't high enough to include them. The 2sc phase is thought to form at intermediate densities, conditions that might exist in the outer regions of a quark star's core. In this phase, red and green quarks might pair, while blue quarks remain unpaired. The color symmetry is broken, leaving fingerprints on the star's properties. But beneath this lies a phase more exotic and symmetrical, the color flavor locked, or CFL, phase. The CFL phase is considered the most beautiful state quark matter can achieve, a perfectly symmetric arrangement where all three flavors of quarks, up, down, and strange, pair together in a tightly interwoven pattern. Each quark flavor locks to a color in such a way that the resulting configuration is uniform, stable, and profoundly different from any known state of matter. In the CFL phase, color and flavor symmetries intertwine, forming a condensate that breaks both symmetries simultaneously. This state has several remarkable properties. For one, it is electrically neutral without requiring electrons. In ordinary neutron stars, electrons are needed to balance charge imbalances among protons and neutrons. In quark matter not arranged in the CFL pattern, electrons also play a crucial role. But in a CFL star, the pairing pattern eliminates the need for electrons entirely. The quark matter becomes self-neutral, simplifying the surface structure and altering the electric fields found above it. The CFL phase is also predicted to be extremely rigid in some respects and extremely fluid in others. It can behave like a superfluid, frictionless and capable of supporting persistent currents, and like a superconductor at the same time. This dual identity makes CFL quark matter uniquely stable. It may be the preferred form of matter at the very highest densities, meaning the innermost core of a quark star could naturally settle into the CFL phase, forming a region of matter denser and purer than anything else in the universe. One of the more intriguing consequences of CFL matter is its influence on neutrino emission. Because the quarks are paired so tightly, many of the processes that normally produce neutrinos are suppressed. This changes the way the star cools. Instead of radiating heat rapidly through neutrinos, a CFL core's cooling slows dramatically once the pairing energy locks in. If an entire star were in the CFL phase, its temperature profile would evolve very differently from that of a neutron star or even a more conventional quark star. The transition to the CFL phase is not gentle. When quark matter cools to the temperature where the pairing becomes energetically favourable, the system undergoes a sharp change, almost like water freezing, but on a cosmic scale. The gap energy associated with CFL pairing is enormous by everyday standards, reaching tens of mega-electron volts. This is millions of times larger than the pairing energies in superconducting materials on Earth. The star's interior reorganizes itself, forming a condensate that spans the entire core. As quark matter cools further, the CFL phase may dominate the entire star, creating an object sometimes referred to as a CFL star. Such a star would differ from other quark stars not only in its internal structure, but also in its emission properties. The absence of electrons in the CFL phase changes the surface's electric field, altering how the star interacts with radiation. The thermal glow of a CFL star might be unusually simple, nearly featureless, smooth, and lacking atomic absorption lines. In some models, the surface could emit photons through processes involving the lightest excitations in the CFL condensate, producing unique signatures in the X-ray or ultraviolet spectrum. A CFL star might also glow faintly through a process involving the breaking of Cooper pairs. In superconductors on Earth, breaking a Cooper pair releases energy in the form of phonons or photons. In CFL quark matter, breaking a quark pair would release energy in the form of quasi-particles associated with the strong force. While these excitations are not photons, the energy they release can cascade into electromagnetic radiation. This could produce a soft, diffuse emission. almost like a cosmic afterglow of the pairing process. Another fascinating prediction is that CFL stars could support color-magnetic flux tubes. Just as ordinary superconductors expel magnetic fields, forcing them into quantized vortices, CFL matter can organize magnetic fields into structured, quantized patterns. These flux tubes may align with the star's rotation, shaping its magnetic geometry in ways unlike any neutron star. The interaction between these flux tubes and the star's superfluid vortices may produce distinctive timing irregularities, glitches or microglitches that follow patterns foreign to neutron star physics. The rigidity of the CFL phase also affects how the star's core responds to external forces. Tidal interactions in a binary system or seismic oscillations triggered by magnetic stresses could behave differently depending on whether the core is in the 2SC phase, the CFL phase, or a mixture. These differences might imprint subtle signatures on gravitational waves from mergers involving quark stars. In principle, future gravitational wave detectors could detect these imprints, revealing the presence of CFL matter through the star's deformation patterns. The presence of strange quarks in the CFL phase also influences the star's chemical composition. In the CFL arrangement, the densities of the three quark flavors are forced to be equal. This equilibrium makes the matter stable in ways that ordinary quark matter is not. It removes instabilities that would otherwise cause the star to oscillate or break symmetry. Some researchers have proposed that the CFL phase is so stable that it could exist indefinitely, making the CFL star one of the most enduring objects in the universe. A particularly striking implication is the possibility that the entire star could be a single, enormous quantum object, one coherent state extending from center to surface. In this vision, the star is not a collection of particles, but a vast, continuous condensate, a cosmic-scale partner to the superfluids created in low-temperature laboratories. Its behavior would be governed by quantum rules across kilometers, miles of matter, a scaled-up version of phenomena normally confined to microscopic systems. Theoretically, CFL stars could even possess unique thermal glow patterns. Because of the absence of electrons and the presence of exotic low-energy excitations, some models predict that CFL stars might shine with a faint, uniform, almost metallic luminosity. Others suggest that their cooling surface may emit subtle variations depending on the pairing gaps and the behavior of the Goldstone bosons within the condensate. In principle, such a glow could stand out from the chaotic emission patterns of ordinary compact stars. Quark matter, already extraordinary, becomes even stranger when paired. The strong force, usually confined to atomic nuclei, orchestrates an entirely new form of order on a scale billions of times larger than any nucleus. Color-superconductivity emerges as the natural consequence of quarks moving freely under immense pressure, forming symmetrical patterns that transform the star's identity. If quark stars exist, and if they reach the densities required for the CFL phase, then somewhere in the universe right now there may be stars glowing softly with the light of a perfect color superconductor, objects whose interiors are locked into quantum harmony, shining with a brilliance not seen anywhere else in nature. For decades, quark stars have lived in the uneasy space between theory and observation. They are allowed by physics, demanded by certain equations of state, and whispered about in simulations, yet no astronomer can point to the sky with absolute certainty and say, "There, that one is made of quarks." Instead, scientists gather hints. They examine anomalies, weird cooling behavior, puzzling mass radius measurements, and stars that spin faster or shine differently than ordinary neutron star models predict. These clues form a growing mosaic, not proof, but the outline of something waiting to be confirmed. The search for quark stars is not like searching for a new species of planet or identifying a distant galaxy. Those objects give clear, visual signals. A quark star hides its identity beneath layers of physics. From the outside, it can look like an ordinary neutron star. The difference lies in subtle patterns, how it cools, how it radiates, how it bends light, how it vibrates when it spins. Observing these patterns requires exquisite precision, instruments that measure microseconds and fractions of photons, telescopes that track X-rays and gamma rays rather than visible light. Across this landscape of clues, several objects stand out, not because they answer the question, but because they refuse to fit neatly into what a neutron star is expected to be. Each represents a small rebellion against the predictions of nuclear matter alone. Each has forced astronomers to ask whether quark matter might already be visible in the sky, disguised as something familiar. One of the most fascinating examples is RxJ 1856.5-3754, a small, quiet object located roughly 400 light-years away in the constellation Corona Australis. It is one of the nearest known isolated neutron stars, and for that reason it became a key target for X-ray observatories. When astronomers measured its thermal spectrum, they expected to see absorption features, spectral fingerprints created by atoms in the star's atmosphere. Instead, they found almost nothing, a smooth, featureless spectrum, a thermal glow without the bumps and valleys that a neutron star's atmosphere would normally produce. This flat simplicity became known as the temperature anomaly. The star appears too hot given its age, yet its spectrum lacks the absorption lines that a neutron star with a hydrogen or helium atmosphere should show. At first, some researchers proposed that it must have a carbon atmosphere, which could smooth out the spectrum. Others suggested a thin, condensed surface, but another interpretation whispered through the astrophysics community. RxJ 1856.5-3754 might be a bare quark star. A bare quark star lacking any atomic atmosphere would emit a nearly perfect black body spectrum, just as this object does. The absence of absorption lines is not a bug, it's the signature of quark matter, and the temperature itself raised eyebrows. RxJ 1856.5-3754 appears too warm for the cooling models of neutron stars of similar age, but fits comfortably within certain quark star predictions. The star became one of the most discussed candidates in the early 2000s, emblematic of how observations can nudge the boundary of theory. Another object with a troubled identity is 3C58. A nebula in the constellation Cassiopeia that contains a pulsar believed to have formed in a supernova observed in the year 1181. If the association is correct, the pulsar is roughly 840 years old, a cosmic infant. Neutron stars that young should still be hot, cooling primarily through neutrino emission but retaining surface temperatures of millions of degrees. Yet observations of 3C58's pulsar showed something astonishing. It appeared too cold. Its X-ray luminosity was lower than expected, and its inferred temperature was far below that of comparable neutron stars. This sparked a long debate. Some argued that the supernova identification might be wrong. Perhaps the pulsar was older than the historical records suggested. Others pointed to rapid cooling mechanisms that could occur in certain nuclear matter configurations. But one explanation stood out. If the star had a quark matter core, or was even a full quark star, it would cool far more quickly than normal. Quark matter emits neutrinos with extraordinary efficiency. Cooling curves that include quark matter drop sharply, matching the low temperatures observed in 3C58 without requiring exotic atmospheric assumptions. The star became a textbook example of how cooling behavior can hint at quark matter. Its existence does not prove quark stars are real, but it illustrates how the universe occasionally presents objects that seem to prefer quark matter math over nuclear matter math. These puzzles accumulate, and each one pushes theorists to refine or rethink their models. Then there is XTE-J 1739-285, a pulsar candidate discovered through rapid X-ray oscillations. It attracted enormous attention because data suggested it may have been rotating at an astonishing rate of about 1,122 times per second. more than 1,000 rotations each second. If confirmed, this would make it the fastest spinning compact star ever observed, surpassing the known maximum for neutron stars in many equations of state. Ordinary neutron stars have structural limits, spin them too fast, and they begin to tear themselves apart. The pressure at their centres must balance the centrifugal forces, and at extremely high spin rates, neutron matter simply cannot remain stable. Quark stars, however, being smaller and more compact, can potentially rotate much faster before reaching their breakup speed. A confirmed spin at 1122 Hz would match beautifully with certain quark star models. The observational evidence for this extreme rotation remains debated, and alternative explanations exist. But the flare of excitement around XTJ 1739-285 showed how rotational anomalies can push the boundary between neutron stars and quark stars. If a star spins faster than neutron matter can theoretically endure, the universe may be signalling that quarks are at play. Beyond these specific objects, the search has expanded dramatically through advances in observational technology. The NICER mission, the Neutron Star Interior Composition Explorer, has revolutionized the way astronomers measure the mass-radius relationship of compact stars. Sitting on the International Space Station, NICER uses X-ray timing to map the surface hotspots of spinning neutron stars, allowing extraordinarily precise modeling of how light bends around them. The bending of light near a compact star is governed by its gravitational field, which in turn depends on both mass and radius. If a star is too compact, too dense, it suggests a softer equation of state, possibly one involving quark matter. NICER's analysis of pulsars, such as PSRJ 0030 plus 0451 and PSRJ 0740 plus 6620, has provided measurements with uncertainties small enough to constrain the physical models of dense matter. Some of the results hint at radii slightly smaller than predicted by many nuclear-only equations of state, leaving room for quark cores. NICER's data on PSRJ 0740 plus 6620 is particularly interesting. This pulsar is massive, around 2.1 solar masses. Many nuclear equations of state struggle to support stars that heavy, but certain hybrid models, where a stiff nuclear shell encases a quark matter core, fit the data surprisingly well. NICER has not proven the existence of quark matter, but the margins it uncovers, the narrow regions where nuclear models begin to bend, are exactly where quark star hypotheses thrive. To interpret all these clues, astronomers focus on several key observational signatures. One is the mass-radius relationship. Nuclear matter has predictable limits. As mass increases, radius decreases, but only up to a point. Quark matter shifts this curve. Quark stars can be smaller for the same mass, or maintain stability at higher masses than neutron-only models predict. Therefore, any object with a radius smaller than about 12 kilometers, about 7 miles, but a mass near or above 2 solar masses attracts immediate attention. Another signature lies in cooling curves. Neutron stars follow a well-understood cooling sequence, initially dominated by neutrino emission and later by photon emission. Quark matter accelerates certain neutrino processes dramatically, causing quark stars or hybrid stars to cool more rapidly. Observations of anomalously cold stars, such as 3C58, hint at these faster cooling mechanisms, particularly when combined with age estimates. Pulse profiles also play a central role. As compact stars rotate, hotspots on their surfaces sweep across the observer's line of sight, creating pulsations in X-ray brightness. The shape of these pulses depends sensitively on the star's compactness, the ratio of mass to radius, and on relativistic effects such as gravitational lensing. By modelling pulse shapes with high precision, astronomers can infer how tightly gravity pulls on outgoing photons. Stars with unexpectedly strong lensing for their measured mass may be more compact than neutron star equations of state allow. X-ray spectra are another vital clue. Ordinary neutron stars possess atmospheres that imprint absorption features onto their emission. These features depend on atmospheric composition, magnetic fields, and surface temperature. But a bare quark star, lacking an atomic atmosphere, would emit a smoother, nearly featureless blackbody spectrum. RxJ 1856.5-3754, with its strikingly simple spectrum, exemplifies this kind of anomaly. Some compact stars exhibit thermal gradients or hotspots inconsistent with crusted neutron star physics. Others show transitions or bursts that hint at exotic interior processes. The diversity of these signals underscores how messy real astrophysics can be. Nature rarely presents clean answers, preferring instead to drop breadcrumbs in different wavelengths, temperatures, and frequencies. One of the most challenging aspects of the search is that each observational signature can have multiple interpretations. A star that cools too fast might have an unusual atmosphere or magnetic field. A star too small for its mass might have unmodelled crustal physics. A featureless spectrum might arise from a condensed surface rather than from quark matter. Even rapid spin measurements can be affected by accretion dynamics or geometric uncertainties, yet the pieces continue to gather. The anomalies accumulate. No single star offers proof, but together they hint at a landscape where nuclear matter alone may not tell the full story. In the coming years, new instruments will sharpen this search. Gravitational wave detectors may capture signals from neutron star mergers that reveal the softness or stiffness of their interiors. If quark matter is present, the merger dynamics will differ. The collapse time, the post-merger oscillations, the ejector composition, all bearing the fingerprints of deconfined quarks. Future X-ray observatories, with higher sensitivity and better spectral resolution, may detect the subtle signatures of bare quark surfaces, or the peculiar thermal patterns of CFL phases. Neutrino detectors may one day capture bursts from a nearby supernova that reveal a phase transition deep within the collapsing core. The question is not whether quark stars can exist, but whether the universe has chosen to make them, and the universe tends to use every path available to it. Somewhere in the sky, perhaps drifting quietly in a faint X-ray glow, or spinning at a rate that challenges the limits of nuclear matter, or cooling faster than physics expects, there may already be a star whose identity we haven't fully recognized, a star that has taken the collapse of matter one step further, a star whose surface is not built from atoms or nuclei, but from the smallest ingredients of existence themselves. The search continues, not because we lack candidates, but because the evidence must reach a clarity that the cosmos rarely grants easily. If quark stars are truly out there, they are already speaking through the anomalies that surround them. It is only a matter of learning to listen with instruments sensitive enough to hear what kind of matter lies within. Compact stars push matter to its limits, compressing the universe's densest ingredients into spheres no larger than a city. But in this tiny arena, where gravity and quantum mechanics wrestle constantly, something intriguing happens. Two stars with the same mass can have very different radii depending on what they are made of. This difference, sometimes only a few kilometers, miles, carries enormous physical meaning. It can determine whether the object is built from nuclear matter or something deeper, like deconfined quark matter. The mass-radius puzzle begins with a simple idea. A neutron star is held up by neutron degeneracy pressure and nuclear repulsion. As mass increases, gravity forces the neutrons closer together and the star becomes smaller. But there is a limit to how tightly neutron matter can be compressed. If you try to push beyond that limit, neutron matter starts to soften. Particles like hyperons begin to appear, weakening the resistance. Eventually, the star collapses into a black hole. Quark matter changes this picture drastically. Because quarks are not confined to individual nucleons in a quark star, they can pack more efficiently. Degenerate quark matter produces pressure in a different way, allowing the star to shrink even further before gravity overwhelms it. The result is a more compact object, denser, smaller, and potentially heavier than a neutron star of the same mass. This is the heart of the mass-radius puzzle. A neutron star of 2 solar masses might have a radius around 12 kilometers, about 7 miles, while a quark star of 2 solar masses might measure closer to 9 or 10 kilometers, about 5.5 to 6 miles. The absolute difference is tiny on a cosmic scale. But observationally, those few kilometers contain the signature of an entire state of matter. The puzzle becomes especially sharp when astronomers observe very compact stars, objects whose inferred radii seem too small for any neutron-based equation of state. Nuclear matter models, no matter how stiff or exotic, often struggle to produce stars below about 11 kilometers without collapsing them entirely. If an object appears more compact than this threshold, quark matter becomes an attractive explanation. This idea has evolved into a broader concept known as the two-family hypothesis. Instead of assuming that all compact stars belong to a single class, this hypothesis proposes 2 distinct families. Family 1, neutron stars, made mostly of nuclear matter, possibly with hyperons or other exotic baryons in the core. Larger radii for a given mass. Maximum mass, typically around 2 solar masses. Family 2, quark stars, or hybrid stars, containing some or all quark matter, smaller radii, potentially stable at masses above 2 solar masses. In this view, the universe does not have to choose one form of matter. Instead, both families coexist. A star born from a supernova might begin as a neutron star, but if its mass is high enough, or its internal density rises due to accretion, it could transform into a more compact quark star. Other stars might be born directly as quark stars if the core collapses past the neutron threshold during the supernova. The two-family hypothesis helps resolve tensions among observations. Many neutron stars appear to have radii around 12 kilometers, consistent with nuclear matter. But others show signs of being smaller, and measurements from NICA and gravitational wave detectors occasionally hint at compactness difficult to reconcile with purely nuclear physics. The coexistence of 2 families provides a natural mapping for this diversity. One of the most powerful observational tools for probing compactness is gravitational redshift. The stronger gravity becomes at a star surface, the more it stretches the light escaping from it. Photons lose energy climbing away from the surface, shifting toward redder wavelengths. This effect is not subtle. For highly compact objects, the redshift can become dramatic. Gravitational redshift reveals how tightly gravity grips the star, which depends on both mass and radius. A very compact star, one with a small radius for its mass, produces stronger redshift than any neutron star model predicts. If astronomers observe absorption lines in the spectrum of a compact star and find them shifted by a higher factor than allowed by nuclear matter, the most straightforward explanation is that the star is more compact than a neutron star can be. This is exactly the scenario quark stars are built for. Though definitive spectral redshift signatures remain elusive, theoreticians often highlight this pathway as one of the cleanest possible discriminators. If a quark star has a bare surface, the emitted photons might show an even cleaner redshift profile, unaltered by atmospheric interactions. Measuring such a shift would be akin to reading the star's compactness directly. A second tension involves heavy pulsars, objects measured at more than 2 solar masses. The discovery of PSR J1614-2230 at roughly 1.97 solar masses, followed by PSR J0348 plus 0432 at 2.01 solar masses, and then PSR J0740 plus 6620 at around 2.1 solar masses, forced theorists to revise many equations of state. Hyperonic models softened too quickly and collapsed below these limits. Some nuclear models also predicted maximum masses that were too low to accommodate these stars. Quark matter provided an elegant solution. Certain quark-based equations of state are stiff enough to support stars up to 2.2 or even 2.4 solar masses. This strengthened the case for hybrid stars, neutron stars with quark matter cores. A core of quark matter can add extra pressure in the center, raising the maximum mass allowed before collapse. Hybrid models also naturally explain why some stars are heavier and more compact simultaneously, but the tension deepens further when comparing different types of observations. Gravitational wave data from the neutron star merger event GW 170817 suggested that at least one of the merging stars had a relatively small tidal deformability, hinting at a compact configuration. Meanwhile, massive pulses observed through radio timing demanded stiff equations of state to avoid collapse. Reconciling these two constraints, softness for compactness, stiffness for mass, becomes difficult if the star is made only of neutrons. But it becomes possible if one of the stars is a hybrid or quark star. In this scenario, the heavy pulsars detected via radio timing represent the stiffest nuclear configurations, while the highly compact stars influencing gravitational wave signatures represent quark-dominated objects. Again, the two-family hypothesis provides a natural mapping between observations that might otherwise seem contradictory. Another clue arises from pulse profiles measured by NICER. As hotspots rotate across the star's surface, the bending of light depends on compactness. Several stars observed by NICER appear consistent with radii smaller than expected from many nuclear equations of state. While analysis remains complex and interpretations vary, these observations continue to nibble at the margins of neutron star viability. They leave open the possibility, sometimes strongly, that quark matter may be lurking inside. The mass-radius puzzle is not just a technical issue in astrophysics, it is a frontier where the nature of matter itself is being tested. If quark stars exist, they reveal that matter has another stable form beyond neutrons. They show that collapse can push matter not into annihilation, but into a new identity. They illustrate how the strong force, normally confined to the hearts of atoms, can govern entire stars, sculpting objects whose compactness betrays their internal state. Somewhere in the universe, stars may already be tracing this boundary, radiating clues through their pulse profiles, cooling curves, and gravitational signals. And in the fine difference between 11 kilometers and 10, or between a redshift of 0.2 and 0.4, may lie the evidence that matter has one more chapter to reveal. A supernova is one of the most violent events the universe can produce, a moment when the core of a massive star collapses and the outer layers are blasted into space in a burst of light brighter than entire galaxies. For centuries, astronomers believed this explosion marked the final exhale of stellar evolution, its ultimate endpoint. But quark matter opens a door to a stranger possibility, that a supernova may not always be the last word. Under the right conditions, a collapsed core could ignite a second explosion, one even more extreme than the first. This theoretical event is called a quark nova. A quark nova begins deep inside a neutron star born from an ordinary supernova. In the aftermath of the explosion, the core settles into a dense sphere of neutron-degenerate matter. For many stars, this is the final form. But if the neutron star is heavy enough, or if it gains additional mass from a binary companion, it may reach densities where neutrons themselves begin to break apart. Their constituent quarks, normally confined in triplets, become deconfined. The core transitions into quark matter. This transition is not smooth. It is a phase change so abrupt and so violent that the structure of the star briefly becomes unstable. The conversion of neutron matter into quark matter releases a burst of energy that, in some models, can rival or exceed the energy of the supernova that created the neutron star in the first place. The mechanism is simple in its outline, but complex in its details. When neutrons collapse into quark matter, they release latent heat and a torrent of neutrinos. If the quark core grows large enough, it reaches a tipping point where the entire star reorganizes itself. The nuclear matter in the outer layers, no longer supported by the same pressure profile, collapses inward and hits the newly formed quark core. This collision generates a shock wave. The shock then propagates outward through the remaining neutron-rich layers, accelerating them into space. The result is a secondary detonation, a quark nova. One of the extraordinary features of this hypothetical explosion is its speed. A quark nova shock may reach velocities far exceeding those of the original supernova ejecta. The neutron-rich material thrown off the neutron star can smash into the slower-moving debris of the earlier supernova, heating it and lighting it up a second time. This re-illumination could create unusual, extremely bright signatures observable from galaxies millions of light-years away. Researchers have proposed that quark novae might explain certain superluminous supernovae, events that shine 10 to 100 times brighter than standard supernovae and remain luminous for unusually long periods. In these scenarios, the initial supernova creates the neutron star and ejects the outer layers of the original star. Days or weeks later, the neutron star undergoes a quark nova. The second explosion injects vast energy into the expanding shell, making it glow with a brilliance that standard models struggle to reproduce. The timing matters. If the quark nova occurs shortly after the supernova, within hours or days, the shock wave crashes into dense material, releasing a burst of radiation that can produce a double-hump light curve. Some superluminous supernovae indeed show peculiar two-peaked brightness patterns, as if they were re-energized after their initial explosion. Another potential signature is found in fast blue optical transients. Brief, extremely hot, bright bursts that fade quickly. These events are difficult to explain with standard astrophysical models, but fit naturally into quark nova predictions. The quark nova ejecta, being rapidly accelerated and consisting of neutron-rich matter, could produce a bright blue flash before cooling, matching the behavior of these enigmatic outbursts. On even more energetic scales, a quark nova may produce gamma rays. When the shock wave forms at the boundary between nuclear matter and quark matter, the extreme densities can accelerate particles to ultra-relativistic energies. In some scenarios, if the neutron star is spinning rapidly or possesses a strong magnetic field, the conversion could produce a short gamma-ray burst. Gamma-ray bursts are among the most powerful electromagnetic events known, and while most are attributed to neutron star mergers or collapses, a quark nova offers an alternate pathway, one that requires only a single star undergoing an internal transformation. Neutrino bursts are another potential signal. During the conversion of neutrons into quark matter, trillions of neutrinos erupt outward, carrying away a large portion of the transition energy. These neutrinos would arrive before the observable flash, just as neutrinos from supernovae reach Earth before the visible explosion. If a nearby quark nova ever occurred, within our own galaxy or a close neighbour, neutrino detectors on Earth might detect an unusual signal. A sudden, intense burst not associated with any known supernova or merger. The neutrino energies and timing would differ from those of standard supernova neutrinos, giving the event a distinctive fingerprint. The quark nova model also predicts unique nucleosynthesis signatures. The ejecta from the second explosion is extremely neutron-rich, potentially ideal for producing heavy elements like gold, platinum, and uranium through rapid neutron capture, the R process. While neutron star mergers are now known to be major sites of this process, quark novae could provide an additional avenue, one that might explain heavy element enrichment in environments where mergers alone seem insufficient. None of these possibilities have been confirmed observationally, and the quark nova remains a theoretical frontier. But the idea continues to attract attention because it meshes naturally with known physics. The transition from neutron matter to quark matter must release energy. Whether that energy escapes gently or violently depends on the star's structure, rotation, magnetic field, and temperature. Under the right conditions, a secondary explosion is not only possible but inevitable. If quark novae exist, they would represent one of the universe's most spectacular displays of transformation. Stars exploding not once but twice, each time shedding a different layer of identity. The first explosion destroys the atomic world. The second destroys the nuclear world. What remains is the quark world, a star stripped down to its most fundamental form. Among the ideas that orbit the concept of quark stars, few inspire as much curiosity and needless anxiety as strangelets. They are hypothetical fragments of strange quark matter, tiny droplets made of up, down, and strange quarks blended into a uniform fluid. If quark stars exist, strangelets are their most portable ambassadors, the smallest pieces of a state of matter that might lie deep inside collapsed stars. The idea begins with stability. If strange quark matter is the true ground state of matter, as suggested by the Bodmer-Witten hypothesis, then small chunks of it could, in principle, exist outside of a star. These chunks would not be bound by gravity, as neutron stars are, but by the strong force itself. The quarks inside would form a tightly packed, self-contained droplet that could remain stable even in vacuum. Strangelets could form in several ways. The first involves the violent birth of a quark star. When neutron matter converts to quark matter during the transformation, the newly formed quark surface may be hot and unstable. Bits of the surface may shake loose, ejecting tiny droplets of strange quark matter into space. These droplets, ranging in size from a few quarks to trillions, would be carried away at high velocity. Another scenario involves collisions. If two quark stars merge, the debris thrown outward could cool into stable nuggets of strange matter. A similar process occurs in neutron star mergers with heavy element nucleosynthesis. In a merger involving quark stars, some ejector might instead condense into strangelets. A stranger possibility arises inside neutron stars containing quark cores. The interface between quark matter and nuclear matter can be turbulent, especially if the star is rotating rapidly or undergoing starquakes. In rare events, small parcels of quark matter might detach from the core and migrate outward. Though this remains speculative, the physics does not forbid it. The question that captured public imagination, especially during early particle collider studies, is whether a strangelet could infect normal matter, converting it into strange matter the way one spark sets off a chain reaction. In the most dramatic version, a strangelet landing on the surface of a neutron star could trigger a collapse, transforming the entire star into a quark star. Or in a more far-fetched version, strangelets created in a laboratory could hypothetically convert Earth's matter into strange matter. The scientific answer is calm, straightforward, and reassuring. No, strangelets cannot infect ordinary matter under normal conditions. The reason is density. Strange quark matter is stable only at extremely high densities, densities found inside neutron stars. At the low densities found in planets, metals, or the air we breathe, strange quark matter becomes unstable. The quark composition depends on pressure. When density drops, the strange quark content becomes energetically unfavorable. The fragment then decays, breaking apart into normal baryons or evaporating into quarks that confine into ordinary particles. This decay process occurs almost instantaneously on human timescales. Heavy ion colliders, such as those at CERN, have investigated this extensively. During collisions inside the Large Hadron Collider and earlier machines like the relativistic heavy ion collider, strange quarks and even small clusters of quark matter appear momentarily, but they vanish almost instantly. Nothing stable forms, the energies and pressures are too low, and the created droplets are far too small to maintain the conditions needed to keep strange matter intact. Astrophysical safety arguments reinforce this conclusion. If stable strangelets were truly dangerous, neutron stars in the Milky Way would frequently convert into quark stars after being struck by cosmic rays containing heavy nuclei. These cosmic rays have energies vastly exceeding what human machines can produce, yet neutron stars demonstrably survive such bombardment for billions of years. No chain reactions, no runaway conversions, no cosmic catastrophes. The universe itself provides the strongest argument. It is filled with neutron stars, millions of them across cosmic time. They exist in dense stellar clusters, in star-forming regions, and near sources of gamma-ray bursts. They are constantly bombarded by high-energy particles. If strangelets were prone to triggering conversions, the galaxy would be full of quark stars already, and neutron stars would be rare. Instead, we observe a familiar population, stable and long-lived. If strangelets do exist, the most they could do, upon encountering ordinary matter, is pass through it, or decay, leaving nothing behind. Outside of extreme densities, their structure simply cannot hold together. Yet the idea remains scientifically fascinating. If detected, strangelets would provide direct evidence of quark matter outside neutron stars, offering a window into the physics of extreme states. Some researchers have proposed searching for strangelets trapped in lunar soil, where cosmic debris accumulates over billions of years. Others have designed detectors capable of identifying unusually dense, high-charge particles in cosmic rays. So far, no definitive strangelet has ever been found. Even without real-world danger, strangelets illuminate something profound about matter. Stability is not universal. The state that is most stable at one density becomes unstable at another. Protons and neutrons are stable at everyday densities, but collapse into quarks at neutron star densities. Strange quark matter may be stable at quark star densities, but unstable in our world. The universe prevents these states from mixing freely. It keeps each form of matter in the environments where it belongs. In this way, strangelets, real or hypothetical, illustrate a quiet truth woven into the architecture of the cosmos. Matter has layers of identity, each one revealed only when pressure, density, or temperature reach the right threshold, and the boundaries between these layers are harder, sharper, and more protective than they first appear. The search for quark stars has always been a game of hints. Cooling anomalies, unusual radii, smooth X-ray spectra, strange rotational behavior. But as new observatories come online, the search is shifting from subtle inference to the possibility of direct identification. The future of quark star detection will not rely on a single instrument or a single method. It will come from the convergence of several technologies, each peeling back a different layer of astrophysical behavior. Together, they may reveal whether the universe truly builds stars from deconfined quark matter. One of the most important tools is NISA, the Neutron Star Interior Composition Explorer. Perched on the International Space Station, NISA has transformed the mass-radius landscape. Instead of relying on crude estimates, astronomers now model the star's pulse profiles with extraordinary precision, tracking how hotspots on the surface sweep across the observer's line of sight. These pulses carry the signature of gravity's strength, how much the star bends its own light, how sharply photons curve around its surface before escaping. For quark star detection, this is invaluable. A quark star is more compact for its mass than a neutron star. This means stronger lensing, sharper distortions in the pulse profile, smaller inferred radii, and a tighter mass radius curve. NISA's measurements of objects like PSRJ 0740 plus 6620 already hint that some stars may be more compact than nuclear physics models comfortably allow. Future NISA datasets, combined with improved modelling of surface hotspots, may push these constraints even further into the territory where quark matter becomes the simplest explanation. But NISA is only the beginning. The next generation of X-ray observatories includes Athena, Advanced Telescope for High-Energy Astrophysics, scheduled to launch in the coming decade. Athena's spectral resolution will dwarf that of current instruments, allowing astronomers to probe the atmospheres, or the lack of atmospheres, of compact stars in exquisite detail. One of the key predictions for bare quark stars is the absence of atomic absorption lines. Quark surfaces, with their thin electron layers, produce nearly featureless spectra. Athena will be able to confirm or rule out these smooth profiles far more precisely than today's telescopes. Athena's calorimeter will also measure subtle shifts in thermal gradients across a star's surface, potentially revealing the difference between heat conduction in nuclear matter and heat conduction in quark matter. The surface temperature distribution of a quark star, especially one in a color-superconducting phase, could differ in recognizable ways from that of a neutron star. On the radio front, the SKA, the Square Kilometre Array, will revolutionize pulsar astronomy. With sensitivity orders of magnitude above current arrays, SKA will uncover tens of thousands of new pulsars. Among them will be the most massive pulsars ever detected, the fastest spinners, and perhaps the most extreme glitching behavior. Each new data point will tighten the boundaries of allowed equations of state. SKA may discover objects whose masses exceed what nuclear matter can support. It may find pulsars spinning so fast that only quark matter cores can maintain structural stability. It may reveal neutron stars with internal vibration frequencies that point to phases of matter softer or stiffer than traditional models predict. Where SKA will excel is precision timing. Small changes in spin rate or pulse shape could betray the presence of quark matter. Sudden frequency jumps, glitches, may behave differently in stars with quark cores, especially if the core is in a color flavor locked phase or contains vortices associated with color superconducting behavior. SKA's sensitivity will allow astronomers to detect microglitches, timing irregularities so tiny they were previously invisible. Some of these patterns may emerge only in stars that contain quark matter. Beyond photons, the new frontier is gravitational waves. When two neutron stars spiral inward and merge, the gravitational waves they emit carry a detailed imprint of their internal composition. The way the stars deform in each other's gravitational field, called tidal deformability, depends sensitively on the stiffness of the matter inside. Neutron stars deform more easily. Quark stars, being more compact and more tightly bound, deform less. The event GW 170817 began to open this window. While the data were limited, the observed tidal deformability was on the low end of predictions, consistent with unusually compact stars. Future detectors will do far better. Upgrades to LIGO and Virgo, and the addition of detectors like CAGRA and the proposed Einstein telescope will increase sensitivity across multiple frequency bands. With these improvements, astronomers will map the deformability curve with unprecedented accuracy. If tidal responses show behavior that cannot be reproduced with any purely nuclear equation of state, the case for quark matter becomes far stronger. Even more dramatic is what happens after the merger. If the merged object survives for even a few milliseconds before collapsing into a black hole, it vibrates violently, sending out gravitational waves in a pattern called the post-merger signal. These vibrations depend on the star's internal structure. A hybrid star containing a quark core will ring differently than a neutron-only object. Certain frequencies will shift or dampen in recognizable ways. Detecting these shifts would be one of the clearest signatures of quark matter ever observed. Quark star mergers may even produce distinct electromagnetic counterparts. If one of the merging stars is a quark star, the ejector composition changes. The amount of neutron-rich material thrown out may differ, influencing the brightness and color of the kilonova. Heavy element production via the R process may follow different pathways. The thermal glow may peak earlier or in different wavelengths. Another avenue for detection lies in neutrino observatories. The conversion from neutron matter to quark matter releases an enormous burst of neutrinos, with energies and time signatures different from those of ordinary supernovae. If a nearby supernova produces a neutron star that collapses into a quark star shortly after birth, neutrino detectors on Earth, like Super Kamiokande, IceCube, or the upcoming Dune Observatory, could capture the signal. A sudden spike in neutrino flux, followed by a suppressed cooling curve, would be a strong indication of a phase transition deep inside the star. Finally, there is the prospect of multi-messenger detection. Gravitational waves, neutrinos, X-rays, and optical signals all telling the same story. A compact star that cools too fast, has an unusually small radius, produces distinctive gravitational wave signatures, and emits a smooth spectrum with no atmospheric absorption lines would be impossible to explain with nuclear physics alone. Quark matter would become the simplest, strongest, and most elegant solution. Across these instruments, NICA, Athena, SCAR, upgraded gravitational wave detectors, and neutrino observatories, the next decades may see the first unambiguous identification of a quark star, not through a single spectacular discovery, but through a convergence of clues: compactness beyond nuclear limits, cooling beyond neutron models, spectra beyond atomic atmospheres, and vibrations beyond conventional matter. The universe may already contain these stars. The technology to recognize them is finally catching up. Matter feels solid to us because it behaves that way at the scale we move through. A table resists our hand. A mountain stands unmoving for millions of years. Even the air around us, invisible and fluid, has weight and pressure we can measure. In our daily world, matter defines boundaries, what we can touch, what we can hold, what we can break. It seems stable, dependable, almost straightforward. Yet this sense of solidity is an illusion born from distance. When we shrink down into the atomic world, the boundaries dissolve. Atoms are mostly empty space. Nuclei are tiny islands suspended in a sea of probabilities. Electrons blur into clouds, push deeper into the heart of those nuclei, and the protons and neutrons fragment into quarks and gluons, entities that seem more like patterns of energy than pieces of anything. Quark stars force us to confront this strangeness in its purest form. Their existence suggests that matter, when compressed far beyond anything found on Earth, sheds every layer of structure we normally associate with it. Atoms vanish, nuclei dissolve. Even neutrons, which we often treat as fundamental enough, collapse into something smoother and more uniform. A quark star is matter stripped of identity. No individual particles, no familiar patterns, just a continuous ocean of the smallest building blocks the universe has ever revealed. It raises a question that belongs as much to philosophy as to physics. What is matter if its most stable form might be a state with no distinct parts? In a human-scale world, identity comes from shape, structure, and separation. A stone is a stone because its atoms cling together in familiar ways. A star is a star because its layers organize heat and pressure into equilibrium. But in a quark star, matter is defined not by form, but by the forces gluing it together. It is a reminder that structure is local, temporary, shaped by environment, and not a universal truth. There is a quiet irony here. The universe creates its largest, densest, and most extreme objects using the tiniest ingredients imaginable. Quarks, entities that can never be isolated, never held, never touched, assemble into stars that can weigh more than our sun. The smallest things become the densest, the least tangible things become the most enduring, and if such a star truly exists somewhere in the dark, it shares an origin with us. The quarks in its core, locked in endless contact under unimaginable pressure, are the same quarks that once drifted freely in the newborn universe. The same kind of quarks that reside in every proton and neutron in our bodies. Across the gulf between human experience and cosmic extremity, we are built from the same ingredients, only the conditions differ. As you close your eyes and let your thoughts drift, it's worth remembering that the cosmos is full of forms of matter stranger than anything we encounter here, and yet all of it traces back to the same early fire, the same expanding universe, the same primordial particles. Even the most alien stars are made of the same stuff that became us, and there is something calming in that. A reminder that in all the vastness and all the strangeness, connection runs deeper than scale. Matter changes its shape, its behavior, even its meaning, but its origins are shared. The universe is built from pieces that tie everything together, including you.